This is joint work with Rula Sharpishkar from Dartmouth and Martin Reinhardt from CISO. So this talk is about a compiler that maps dynamical systems, which are systems of differential equations, onto programmable analog devices, which are a new class of computing platforms. The main contribution of this talk is the Arco compiler, which automates this process. To contextualize my contribution, I will first briefly discuss dynamical systems, and then I'll discuss our target class of hardware platforms, analog devices. So a dynamical system is a set of differential equations that define dynamics over state variables, where a state variable models some physical quantity. This physical quantity can be a concentration of a molecule, a position, or a charge in an electrical component. The differential equations of the system specify the continuous dynamics of the state variables over time. Dynamical systems are used to model a wide range of physical phenomena from domains such as chemistry, electrical engineering, biology, and aeronautics. But for the purposes of this research, we will focus on biological dynamical systems. Specifically, we will focus on cellular dynamics, including modeling gene-protein networks, biochemical processes, and signaling pathways. So what people typically want to do with a dynamical system is they are interested in simulating it. A dynamical system is simulated by computing the values of the state variables over time. The evolution of these variables provides insight into the behavior of the physical system you are modeling. Of course, people have needed to simulate dynamical systems for longer than there have been digital computers. In fact, in the 1950s, people built primitive analog computers to simulate dynamical systems. For example, there was the Telefunken RAT 700, which was used to simulate dynamical systems in the 1960s. In the image below, it is actually configured to be running a car suspension simulation. Researchers ran simulations on machines such as the Telefunken by directly mapping the dynamical system they had onto the analog computer. The state variables in their system were mapped to properties of wires in the circuit, such as voltages and currents. And the circuit dynamics directly corresponded to the system dynamics. The way researchers would do this is they would come up with a circuit, and then they would connect primitive components, which were usually resistors of varying resistances or inductors, together through a patchboard of the analog computer. This was no small feat, as the patchboard was sometimes the size of a room. Once the problem was completely mapped, simulating the dynamical system simply became a matter of turning on the circuit and running the circuit over a period of time while listening in on some wire with a voltmeter or an ammeter. Analog computers, such as the Telefunken, faded from popularity and the field entered the age of digital computing, where it has been for the last few decades. As the advances in digital systems have slowed, hardware researchers have actually started revisiting analog computation as a potential solution for simulating dynamical systems. Today, we have new analog computers. These devices exploit all of the advances in semiconductor technology over the last several decades and are in themselves solid-state devices. More importantly, they offer a host of significantly new capabilities. They contain complex, powerful, heavily optimized analog building blocks. They are digitally reprogrammable, and they have the ability to amplify and exploit analog noise, turning noise from a bug that was undesired into a feature that can actually be used in the computation. These new analog devices are particularly well suited for computations that involve differential equations. They allow for you to run the differential equations continuously and directly map the dynamics, as well as provide a means for you to model stochastics of the system you wish to simulate. They also have the added benefits of being energy efficient and fast. What does it take to manually program these devices, though? Well, for one, you need domain expertise because you probably designed the dynamical system you wish to simulate. You also need hardware expertise because you need to understand how to program the analog device. And you also need the ability to manage details. A mistake made in configuring the device basically means the programmer must debug a set of differential equations that are incorrectly implemented. Even for someone who has worked intimately with these dynamical systems and with the analog hardware for years, it takes somewhere between 4 to 8 hours to program a very simple system of just 4 differential equations. Like any compiler, the Arco compiler works with an abstraction of the analog hardware. Standard compilers for digital systems target a standard ISA, which is an abstraction of the digital hardware. Our analog hardware also has an abstraction, but it is very different from the abstractions you see with digital machines. So let's take a closer look at the abstraction for programmable analog devices. A programmable analog device exists within a larger digital computing environment, where the digital computing environment can provide inputs to the analog device through the input components, or the digital to analog converters. The surrounding digital environment may also read values from the analog device using the analog to digital converters, or the output components. The brunt of the computation is performed by connecting together the analog computation components to run the simulation you desire. Each analog computation component is in itself an abstraction over sets of transistors. The computational component has input ports which may participate in dynamics as a voltage or a current. Each computational component also has output ports, whose voltage or current is the result of the computation. The dynamics of the properties of output ports are defined as a set of equations. And now you can see why analog computing is such a great platform for implementing dynamical systems. They directly implement the kinds of continuous dynamics that are necessary to model differential equations accurately. The relations that govern these dynamics of a port property could be a function of the current of an input port, or the voltage of an input port, or even a property of another output port. What this does is it creates a cyclic dependence between output properties. In this particular case, the cyclic dependence is caused by feedback within the analog circuit. So now that we have this programmable analog device, let's go over the two ways you program this device. The first thing you can do is you can supply values or variables into the digital to analog converters. This is called mapping the variable or value. The second thing you can do is you can connect ports of components within the analog device. This is called the connection. So now that we understand the abstraction the compiler is working with, we can now talk about how the compiler maps the dynamical system specification onto an analog device. So the first step that Arco compiler takes is it selects an equation from the dynamical system. So if we have the following set of equations, for this example, let's select the variable s, the equation that defines the dynamics of variable s. The next thing we do is we select the hardware, specifically the property of the port of the component that we are interested in. So we have all of these components to choose from. We choose the RxN component. More specifically, we choose the voltage of port A, which is an output port in this component. So now our problem becomes mapping the dynamics of S onto the voltage of output port A. And the way we do this is we use a process called unification. So the general idea is as follows. You would like to map the dynamics of the variable in your dynamical system to the variable in your hardware component. And what you need to do is you essentially need to unify the dynamics of these two quantities. So you can see basically what you need to do is fill in expressions, assign values to the voltage of A naught and the voltage of C, such that these expressions are equal. You can see that if you assign S tot to the voltage of A0, and if you assign ES to the voltage of C, you make these two expressions equivalent. But this creates a complication, because now CV and ES are entangled. And this brings us to the concept of relation entanglement. What this means is that the hardware specification basically states that CV has a certain set of dynamics. And we know ES also has a set of dynamics from the dynamical system we're trying to simulate. By saying that CV is mapped to ES, what we're saying is that CV simultaneously has to have two separate sets of dynamics. So the way you resolve these entanglements is you detangle the variables through the process of unification. So if we look at our block, which we had before, and we perform the initial unification, we perform this unification to detangle the two variables, what we get is 4 new assignments over the block. This creates another entanglement between the variable E and the voltage of port B. So B, V, and E are entangled. And we do another unification to resolve this entanglement, and we come up with an assignment for the last port. So now we have this RxN block that is specialized to model ES, S, and E, which were the variables in our dynamical system. But we cannot supply the inputs to this block directly from our digital system. What we need to do is we need to use the input components. So an input component, or a DAC, converts a sequence of digital values to a voltage or a current. So the first thing you do is you choose the values you'd like to assign to the DAC, and then you wire the analog outputs of each of these DACs to the ports that you would like to supply the values to. Similarly, if you would like to measure a value from your analog device, you use an output component, or an ADC. This output component converts the voltage or current to a measurable sequence of digital values. So to finish this off, to model Q plus K0, we simply use a current adder and 2 input components. So now I've explained at a high level how the Arco compiler maps dynamical systems onto the analog hardware. We are now ready to cover exactly how Arco performs this mapping. So what Arco is it is essentially a search over tableaus, where a tableau is the hardware state and all of the remaining goals in the system. In this context, a goal is an unmapped expression or relation. The general search algorithm is you start with an initial tableau, and then what you do is you apply tableau transitions over the initial tableaus until you find a solved tableau. So the initial tableau is comprised of a set of goals. In this case, our single goal is S equals 2 times T. The goals are essentially your dynamical system when you start out. You also have your set of available hardware. When you're starting out, this is all the hardware on your analog device. Finally, you have your constrained hardware and the configuration that you are building. Since we have not done any transitions, our configuration is empty and the constrained hardware is empty. We know when we are done, when the set of goals is empty. The configuration, the subsequent configuration is therefore our solution configuration, and it successfully maps the dynamical system from the dynamical system onto the analog hardware. To transform the initial tableau into the goal tableau, what you do is you apply tableau transitions, of which there are 3. There's the unification transition, the connection transition, and the variable mapping transition. The unification transition is the most important transition of the 3, and it essentially takes us from, if you remember the previous example, initially mapping S to the voltage of A, all the way to having a fully configured RxN block. So essentially, this is the semantics for the unified transition. What you do is you start out with this initial tableau, with this tableau, which is in this case an initial tableau, and you select a goal in your set of goals. There's only one goal in this case, so we select S equals 2 times T. We then select a hardware relation to unify the goal against. In this case, we are going to select the current of B equals 2 times the current of A. What we then do is we invoke the unification routine. The unification routine has its own set of semantics, which are detailed in the paper, but essentially you can think of it as this oracle that does this unification, detangles everything, and produces a new set of available hardware, a new set of constrained hardware, and your new set of goals. So to break down what it generated, remember you're doing this mapping process of S equals 2 times T to the current of B equals 2 times the current of A. So if you remember, we initially had this S equals 2 times T goal in the goal column, but it went away because we performed the mapping process. The mapping process yielded these 2 assignments, with the assignment that maps T to the current of A, and the assignment that maps S to the current of B. We also had this hardware relation, the current of B equals 2 times the current of A. But since we generated these assignments, what we have effectively done is we have constrained the hardware. These constraints essentially mean that the dynamics of the current of B are now such that the current of B is S, or the current of B is 2 times T, where T is mapped to the voltage of A. Similarly, we actually had an unused output port. We had the current of CI equals the current of AI over 2. But since we have performed mappings over A and B, and CI equals AI over 2, what that means is CI now equals T over 2. So in this partially constrained hardware column, you can actually reuse this partially constrained hardware later in the solving process. What you then do, once you have this updated set of available hardware, partial hardware, and goals, is you build a new tableau out of it. So now we will discuss the next transition, which is the connect transition. This is one of the 2 transitions that starts building your hardware configuration. The general idea is you have 2 ports you would like to connect, and you simply make a connection between them. So again, here are the semantics of the transition. What it does is it looks for a goal of the form some property Q of an input port equals some property Q of an output port. It then finds the corresponding wire. In this case, it is satisfying the goal, the current of A equals the current of Z, and it found the wire ZA, which fulfills this goal. It then removes both the goal and the wire and adds the connection to the configuration column. The final transition is the variable mapping transition. What this transition does is it essentially maps a value to the digital interface of a DAC, or an input component. So the general formulation is, it looks for a goal of the form, the digital interface of port X, for example, equals the variable T. So it finds this goal, and then all it does is it performs the mapping. So it just adds the mapping to your configuration. So this set of transitions essentially just describes the space that we are searching over from the initial tableau. So now we're going to go into brief detail about the algorithm that we use to explore this space of transitions. So essentially, like many search algorithms, this search algorithm maintains a frontier, which is a set of tableau configurations to explore. This frontier starts out with only the initial tableau in it. And essentially, while there exists some tableau in the frontier, it chooses a tableau, and if the tableau is solved, it returns the configuration, because this means that you have finished and you found the correct configuration. Otherwise, what it does is it selects a set of transitions to take from the tableau it has picked, and then it creates a new set of derived tableaus that can be derived from this tableau using a transition. It then removes the current tableau from the frontier and adds a set of tableaus as the drive set Tableau to the frontier. As with every search algorithm, this search algorithm implements a lot of optimizations. There are two optimizations that are part of the core search algorithm. There's the choose heuristic, which determines how you choose the Tableau to work on. The heuristic we use is essentially we choose the lowest complexity Tableau configuration of a set of tableaus. The next heuristic we use is the heuristic that chooses which transitions to select of all the transitions that you can take from a Tableau. So our selection process basically prioritizes simple goals, transitions that solve simple goals, because the rationale there is if you were unable to solve a connect or a mapping goal, that whole subtree of the search is going to be difficult to fulfill. We also implement several other search optimizations. We, for example, aggregate classes of components, meaning that if you have multiple instances of the same component, it'll aggregate it as a single aggregate component. What this does is it drastically reduces the search space we explore. However, it does introduce instance constraints that must be handled separately. We also perform caching of partial configurations, and we utilize a compact search tree data structure to reduce our memory footprint. So here's the evaluation. We implemented the Arco compiler. We specified some analog hardware and selected benchmarks from the biomodels database. We then synthesized hardware configurations from these benchmarks, and we analyzed the configurations. So the hardware components we used in our analog device are a selection of analog components from collaborators, textbooks, and publications. The dynamical systems benchmarks we selected are published artifacts from well-cited computational biology papers from the biomodels database. To give you a feel for what these benchmarks are doing, one benchmark in particular, the apoptosis benchmark, models a signaling pathway for which unfolded proteins can trigger a decision process that sometimes results in cell death. This is a critical part of cell biology and has a role in neurodegenerative and cardiovascular disease, diabetes, and kidney diseases. This particular model has 27 differential equations and 48 straight-line equations that model this behavior. In general, our benchmarks have anywhere between 4 to 27 differential equations and 0 to 48 straight-line equations. Now that we had our benchmarks and our analog hardware, we then used the Arco compiler to synthesize configurations that model the dynamical systems from the biomodel database. So the configurations we synthesized have anywhere between 10 to 600 connections and 28 to 350 components, where 7 to 147 of them are analog components. Most interestingly, our configuration makes use of a wide variety of the components available to it, and in the apoptosis case, actually uses one of each component that is available. Arco is able to synthesize these configurations at a rate that is roughly linear to the number of equations in this dynamical system. At least that's what we observed empirically. To give you a feel for the kinds of patterns that it used to synthesize certain equations, take this example of the perk to the -4 term in the apoptosis benchmark. So this is a seemingly simple term that essentially is a negative exponentiation of the perk variable. However, in analog devices, it is not common to offer an exponentiation block in the analog device. Instead, there's this switch block, which is a more complicated relation. So what Arco figured out is it figured out how to chain a current adder to a switch block and set the parameters in both the current adder and the switch block, such that the resulting expression, when simplified, produces perk to the -4. Here's some related work. There's been some work on using analog neural network accelerators for approximate computation. The basic idea here is to find subcomputations of standard digital computations that implement these subcomputations using approximate neural networks. Here are some of the differences. The related work does subcomputations of digital systems, whereas we map an entire dynamical system onto the hardware. They do approximations of digital computations, while we do an exact mapping of dynamical systems. We target analog hardware for dynamical systems, and they target analog hardware for neural networks. There's also been some work on discrete models, which are formalisms for modeling digital computing systems repurposed for modeling biological systems. These models model the causality of the events instead of directly modeling time. Since Arco works with differential equations, time is actually explicitly modeled. These discrete models typically use general-purpose discrete digital hardware, whereas we make use of the energy-efficient analog hardware to perform our computation. Here's the conclusion. We've been using the same model of computation for the last half a century. There's a lot of interesting research in this area, but now it's time to move on and look forward. Programmable analog devices are a new and powerful model of computation. They afford powerful and energy-efficient computing primitives, and already have a compelling initial application, biology. Now, the great thing about these programming language techniques is that programming language techniques, including language design, synthesis, compilation, and even static and dynamic analysis, as the key technology for enabling us to unlock the potential of these new platforms. We have presented the first compiler for this platform, and you have to realize that there is a lot of, this is a very deep research area, and there are decades of new and compelling results. Thank you.
If you have any questions, could you please come down and use the microphone? Actually, I do have one question. So you mentioned that Arco has the ability to use partially constrained blocks again.
Yes.
How often does that actually occur in practice? Is that something you see frequently, or is this, seems like this would be some parameter of the ability for the system to minimize the number of components that are used in the synthesis?
Yes. So I mean, eventually we would like to essentially constrain the system to use a minimal number of components, and then what it can do is it can reuse the relations that are partially constrained.
Okay. Have you seen that in some of the benchmarks in practice?
Yeah, we've seen that on Arco.
Okay, interesting.
Great talk.
Thanks.
I'm really interested in sort of like compiler transformations, So compiler transformations, are there any that you can do in this sort of system, an analog system?
So you're talking about optimizing the differential equations?
Yeah, so you talk about, in your search algorithm, you are selecting the least, or you're choosing least complex tableaus first.
Oh, yeah.
Are there any other optimizations that you foresee being possible in these sorts of hardwares?
Oh yeah, there's a lot to be done. I mean, as we were developing the system, we found that there were a lot of different kinds of optimizations we could implement. And yeah, there's basically a lot of performance on the table. Yeah.
Hi. So this, a lot of things about this talk reminded me of relational programming, where you don't differentiate between inputs and outputs. And so I'm wondering if you can comment on that at all. And also especially, so in relational programming, you have this phenomenon where divergence is pretty common. And Wilbert called it the divergence crisis at one point. So I'm wondering if that's the case here. Like if your compiler ever can't find a solution, if it's ever non-terminating.
Okay, so if I understand correctly, okay, let me think about it for a second. So I mean, we do delineate between inputs and outputs in the dynamical system as well, right? Like basically the output ports of components are consistently mapped to outputs, initially mapped to outputs in the dynamical system. Can you elaborate a little bit on the relational programming?
It seemed like there was a relationship, and I guess I'd like to talk with you more about it later.
Yeah, let's talk about it.
Okay, cool, thanks.
Questions? If not, let's thank the speaker for the travel stuff. Thank you so much.